In this video we are going to solve some examples on the case of exact first order first degree ordinary differential equation. So let's assume that we have a first order first degree differential equation of this form: m of x and y dx plus n of x and y dy equal to 0. The first thing that we need to do is first to check for exactness, and to do this we check if partial m by partial y equal to partial n by partial x. If this is satisfied, then the ordinary differential equation that we have is exact ODE, and this means that we guarantee the existence of a solution for this differential equation of this form: u of x and y equal to constant. And how to find this solution? We do this is the next step. We say that partial u by partial x equal to the function m in the differential equation, and partial u by partial y equal to the function n of x and y in the given differential equation. And from these two formulas we solve for the function u of x and y by integration, and then we find u of x and y, and we take this one here to substitute in this formula to obtain the general solution of the first order differential equation. And the last step that we need to do is to check for solution, and to do this we differentiate this function that we get here. So we say du will equal to partial u by partial x dx plus partial u by partial y dy, and this will equal to 0. If our solution is correct, then we will find that partial u by partial x that we get here is exactly equal to m of x and y in the given differential equation, and we will also find that partial u by partial y that we get here is exactly the same as n of x and y in the given differential equation. And these are the three steps that we need to find the solution of first order first degree differential equation. So let's take an examples to clarify this technique. Let's see that we have differential equation of this form: 2xy dx plus x square plus cosine y dy equal to 0. When you compare this to the standard form that we have discussed before, so this here will be our function m of x and y, and this one here will be our function n of x and y. So the first step is to check for exactness. To do this we find partial m by partial y, and here in this case it will be when we differentiate this term here by with respect to y, we will get 2x, and we find partial n by partial x, so we differentiate this term here with respect to x, and we will get 2x, and when we differentiate cosine y with respect to x, we will get 0. So the total differentiation of the function n with respect to x is just 2x. And here by comparison we can see that partial m by partial y is equal to partial n by partial x, and so the differential equation is exact. So this means that we guarantee the existence of this solution u of x and y equal to constant. Now we will go to the next step to find this function u. So we will say, so this is the next step, that partial u by partial x will equal to the function m, which is 2xy, and also we will have partial u by partial y will equal to the function n, which is x squared plus cosine y. Okay, so from this one here we can find the function u of x and y by integration with respect to x. So we will deal with y as a constant, and in this case we will get u of x and y is equal to the integration of this term 2xy dx plus the constant of integration. And since we only integrate with respect to x, and we deal with y as a constant, so the constant that you get here, it might be constant or function of y. So we will make it general, so we will make the constant here of the integration is some function of y. So this will give us, when we integrate this term here with respect to x, keeping y constant, we will get here the integration of x will be x squared over 2, and here multiplied by 2, so we will get x squared y plus f of y. Once we get this, so this is our function u of x and y. Once we get this, we differentiate this one here with respect to y. So we say partial u by partial y. And this will give us, here when we differentiate the first term here, we will get x squared. And when we differentiate the function f of y with respect to y, we will get f dash of y. And we take this result here to this formula. So now we know what is partial u by partial y, and here the right hand side will be x squared plus cosine y. So when we feed this result into this equation, we will say that x squared plus f dash of y equal to x squared plus cosine y. And so we say that f dash of y will equal to cosine y. And so by integration we will get, when we integrate both sides, we will have f of y will equal to the integration of cosine y, which is sine y plus some constant, let's call it a, for instance. So now we have determined the function f of y, and so now we can write the complete definition of the function u of x and y. So we'll say that u of x and y will equal to x squared y plus fy, which is now sine y plus some constant. Now we need to be careful because u of xy is not the solution. Remember, our solution is this one. So this is the general solution. So we need to say that this u of xy is equal to this constant, and this will give us the general solution of the differential equation. So we'll say that this one here is equal to c, and so we will say that x squared y plus sine y will equal to c minus a, because here we will transfer a to the right hand side, and so we will get c minus a, which can be written as one constant, which is, let's call it p. So this is our general. So this is our general solution of the given ordinary differential equation. The last step is to check for the solution, and the check here is to differentiate this given solution with respect to x, and we differentiate it again partially with respect to y. If our solution is correct, we will get the same functions m and n. And if we look here, we will have partial u by partial x. When we differentiate this one here, we will get 2x y, and partial u by partial y will be, the first term here will be x squared, and the differentiation of sine y with respect to y will be cosine y. So if we compare these two results with the given function m and n, we will find that partial u partial x equal to m and partial u partial y equal to n, and so our solution is correct. We can solve the same example here by shortcut technique, and this can be done by grouping the terms and by inspection. And this is really comes from the fact that the exactness of the differential equation means that this differential equation here represents an exact differentiation of some function u of x and y. So we can use this definition to find this u of x and y directly. So the first step will always be is to check for exactness, and we already have done this, and we found that this differential equation is exact. So we can group the terms together to find the function which by differentiation will give this differential equation, and this will be x squared y. So by differentiating this term here with respect to x, will give us this function m of x and y. So the next step that we need to make sure that is by differentiating the function, will we get this function n of x and y or not? We will find here if we differentiate this term with respect to y, we will get x squared, which is this one here. So we are fine here with this term, but we can't get this term of cosine y, and so it means we need another term for this cosine y. So we need another term which by differentiation with respect to y gives cosine y, and this one here will be sine y. So if we look at this function here, if we differentiate with respect to x, we will get 2xy. So this is our function here, m of x and y. And if we differentiate this function here with respect to y, we will get x squared, and the differentiation of sine y will give us cosine y. And so this differential equation represents the exact differentiation of this function. And so we can find the solution directly by direct integration for both sides, and from this we get x squared y plus sine y equal to some constant, and this is directly the solution of the differential equation. And we already have done our check in the way, because now we know that for sure if this function is differentiated with respect to x, will give us this function m of x and y. And when we differentiate this one here with respect to y, we will get this function here n of x and y. So this is a shortcut method, but sometimes maybe you can't figure out which function is this. In this case, you can follow the systematic approach by saying that partial u by partial x equal to m, which is 2xy, and partial u by partial y equal to n, which is x squared plus cosine y, and you integrate this one here considering y as a constant to find the function u of x and y. And after that you differentiate this one here to find partial u by partial y, and then you compare this result with this right hand side of this formula to find the constant function of y, and then you get the solution of the differential equation as we have done before. Let's take another example. If we have y dash equal to x y squared minus 1 over 1 minus x squared y. The first thing here that we need to do is to put this differential equation into our standard form in this way: m of x and y dx plus n of x and y dy equal to 0. And this is pretty straightforward. We say that y dash is dy by dx, and this will equal to x y squared minus 1 over 1 minus x squared y. And by multiplying both sides together and put everything in the left hand side, we will have this one here multiplied by dx, so we will have x y squared minus 1 dx. This will equal to 1 minus x squared y multiplied by dy. And if we move this one here to the left hand side, we will have x y squared minus 1 dx plus, we will change the sign here of this term, so we will have x squared y minus 1 dy equal to 0. And this matches the general form of the first order first degree differential equation. And from this form here, we have this one here is our function m of x and y, and this function here is our one n of x and y. So the first thing that we need to do here is to check for exactness. So this is our first step. So we say partial m by partial y. This will give us here, when we differentiate this term with respect to y, we will have 2xy. And partial n by partial x, when we differentiate this term here with respect to x, we will get 2xy as well. And we can see that partial n by partial y equals to partial n by partial x, and so this is an exact first order first degree differential equation. We can follow the systematic approach as before, or we can solve it directly using the shortcut technique. We will use the shortcut here in this method. So we will say here, so we are looking for the function. If we look at this one here, the logic result that we can think of for this one here is to be 1 over 2 x square y square, and to get this one minus 1 here, so it will be here minus x. Now if we look at this one, if we differentiate this one with respect to x, we will get here 2x multiplied by 1 over 2, so we will get xy squared, so this is correct. And when we differentiate this one here, we will get minus 1, so this is correct. Before we close the parentheses here, we need to make sure that the differentiation of this function will give also the function n of x and y. So if we differentiate this term here with respect to y, what we will get here? We will get 2y, and here we have 1 over 2, so it will be x squared y, which is exactly the first term here, so we are fine here. And if we differentiate minus x with respect to y, we will get 0. Okay, so that's fine, it doesn't affect the result here. But here we still have minus 1 in this function here, which we couldn't get from only these two terms. So we need to consider an extra term here to find this one, to find the minus 1 when we differentiate this function with respect to y. And this will be minus y. So now we can close the parentheses. So if we close the parentheses now, and we see that this one is equal to 0, now if we differentiate with respect to x, we will get this function m, and if we differentiate with respect to y, we will get our function n. And so we can get the solution directly of this differential equation by direct integration of both sides, which gives us 1 over 2 x squared y squared minus x minus y equal to constant. And this is our general solution of the first order, first degree differential equation that we were dealing with in this example. Of course, I encourage you to now to try the second way around, to try to find the solution here by using the systematic approach. So once you are sure that this is exact differential equation, you see that partial u by partial x will equal to the function m, so this will equal to x y squared minus 1, and partial u by partial y equal to the function n, which is x squared y minus 1. And from these two formulas you try to find the function u of x and y, and then you finally see that this u of x and y that you get is equal to c. And look if you get the same solution as this one here or not. Of course, if you follow the same technique, you will get exactly the same results. I hope this was clear, and thank you for watching.